All right, at the end of last class, which was last Wednesday, we went over the properties for logarithms, and we're going to now put those logarithms together on how to use the sum and or the quotient and the product rule for logarithms, as well as the power rule for logarithms, in order to expand and contract logarithmic expressions. So, how do we do this? Well, we're going to take anything that is a product within a logarithmic function, and that's going to turn into a sum of logarithms. And anything that is considered a division, a quotient, will turn into a difference of logarithms. So we can apply more than one rule here all at the same time. Essentially, anything that's multiplication, so like the x to the fourth times the square root of y, that's going to turn into a sum of logarithms. And this quotient here, where we divide by 7, that's going to end up being a subtraction, a negative logarithm. So I can write this natural log of x to the fourth square root of y divided by 7 as a sum and difference of multiple natural logs. So we'll have natural log of x to the fourth plus natural log of square root of y minus natural log of 7, right? Anything that's a product becomes a sum. Anything that is a quotient becomes a difference. And then we can use the product, sorry, not the product, the power property, the power rule for logs, to take any kind of exponent that we have and move it in front of the logarithm. So we're going to take any power, including the square root, because we know we can write the square root as a 1/2 power. So I might go back and fix this and say this is actually y to the 1/2 power. Right, and in doing so, I can now use the power rule to take this 1/2 in front of this logarithms. So we're going to have the 4 come in front of this natural log of x plus 1/2 of the natural log of y minus the natural log of 7. This is now a fully expanded logarithmic expression, right? We started with a single log with things multiplied with exponents and divided. We now have simply just a sum and difference of very basic natural logs, right? The whole purpose is to simplify the logarithmic expressions so that they have a single term inside of them, right? Whether it's x or y or 7, there's no more exponents, there's no more products, there's no more quotients. So that's how we expand. So when you see the word expand, you're aiming for multiple logs added and subtracted. On the next page, we're going to talk about how to go backwards, how to start with something that is a multiple natural logs or logs added and subtracted, and go back towards a more condensed expression, which is why we call it condensation. So when it says to condense an expression, we're actually going to work everything backwards the other way. Let me actually not do that one. I will do. No, I'll do this one. That's fine. So, what does it mean to condense? Well, we're going to do everything backwards, which is the first thing we're going to do is we're going to take all of these coefficients and we're going to pop them up into the exponents of whatever is inside each logarithm, so that we may have the logs, just the logs added and subtracted from each other. So when we rewrite this first term here, the 2 log base 2 of x, will become log base 2 of x squared. Right? And then the 1/2 will go up and be an exponent, so that'll be a log base 2 of x minus 1 to the 1/2 power. And finally, minus this 3 is also going to become an exponent. So we'll mark these as becoming exponents. That'll be log base 2 of x plus 3 squared and then that's raised to the third power. So that's where the 3 goes. Right, so I have this 2, this 1/2, and this 3. Are now exponents in the next step. And now there's a couple of things to pay attention to. There are no more coefficients. They're all multiplied by 1 in front. And all of the bases for the logs are the same. You can only condense when the bases are the same, when you have the same type of log added and subtracted. So if I have log base 2 added to another log base 2, subtracted to another log base 2, we can condense all of that into a single expression that has just one log base 2. But before I do that, I kind of want to rewrite this 1/2 because I don't like fractional powers, and I do want to deal with this exponent raised to another exponent deal in the last term. So how do we deal with that? Well, we leave the first one alone. That's a log base 2 of x squared. That one is totally fine. A 1/2 power we saw on the previous problem as well is a square root. So we're going to say log base 2 of the square root of x minus 1. Right, that looks a little bit neater, written as a square root. And then finally, when I have an expression raised to a power raised to another power, we're going to multiply those exponents. These are laws of exponents that you should know at this point. So that'll be x plus 3 to the 6th power, because when you raise an exponent to another exponent, we multiply those. Or when you raise a term of expression to an exponent and then raise that whole expression to another exponent, we multiply them. So now it's in the most simplest form for each log. And now we're going to condense all of this into a single log base 2 expression. And this log base 2 expression is going to have some products and quotients because we're going in the other direction, we're condensing. So the best way to do this is to take any log that's positive, like this log and this log, and put those in the numerator, because we know there's a minus in here somewhere, so there is going to be a fraction of some kind. Best way to do this is any log that's negative, the expression inside of the log is going to go in the denominator. So we're going to take this expression, and that's going to go in our denominator. So x plus 3 to the 6th power will be my denominator. And then anything, any positive log expression is going to end up being a factor of the numerator. So those two, the x squared and the square root of x minus 1, so x squared and the square root of x minus 1 will both be numerators, and those are multiplied together. All right, so we end up with a single logarithmic expression with things in the numerator and in the denominator. Note that this first log, I said any positive log, such as this one, goes in the numerator. Note that this first one is also a positive log because there is no negative sign in front of it, right? There's just a 1 in front of here, and that's a positive 1. So that expression inside of that log will end up in the numerator. Okay, are there any questions on expanding or condensing these expressions? Okay, you guys can attempt the rest of those. We also have a change of base formula for logarithms, and I'm going to jump straight to here. This is your change of base formula, and you'll notice that from the left side of the expression to the right side of the expression, the base of the log has changed. All right, so you can take any log base, let's just say log base b, and we can convert that to any other base that we'd like. Generally, we like changing to the standard log, which is log base 10, but we don't need to write the 10 because there is a, if we just write log, it's understood that it's log base 10. Generally, we change to either the standard log or the natural log. So when you're applying the change of base formula, you generally are going towards natural log or standard log, but there may be niche situations where you want to change to like a log base 7, for example, because maybe M is a nice power of 7 or B is a power of 7. Either way, when you see certain powers, there may be niche situations where you want to switch to a specific log base, but generally we switch to either log base 10 natural or log base 10 or the natural log. Right. So if we want to change this kind of expression, log base 5 of 3. By using the formula, it wants us to change it to a quotient of natural logarithms. So we're going to focus on this change of base formula, which is essentially the same as this. But if you want to use natural logarithms, you can just replace these with natural logarithms. Right? But the same rules apply. We're going to make a fraction, a quotient, and we're going to do natural log of m, which was whatever was inside of this log. So it'll be natural log of 3 divided by the natural log of 5. So we take the natural log of what's inside the log, and then we take the natural log of the base. So that is how to apply the change of base formula. It's pretty straightforward. You turn a single log into a quotient, with the numerator being the number inside the log, and the denominator being the base of the log, of the original log. I think there's a question on your worksheet from last time that asks you to, is there one? Yeah, rewriting as a logs using base 10. Yeah, number 5 on last week's worksheet is using this formula. So if you haven't done number 5, you'll do that today. And then also number 7, like I said last time, is going to be done after we go over 7.6 today. So let's move on to 7.6, which is working with equations involving exponents and logarithms. Equations meaning equalities. Now we're no longer working on single expressions and just manipulating, expanding, condensing, rewriting in terms of an exponential if it was a logarithmic or vice versa. We were working with single expressions before this. Now we're going to talk about equations, which means we have some kind of equality and something we're trying to solve for. The first tool in solving equations is going to be using like bases, meaning if you have the same base on both sides, so in an expression like this where you have b raised to some power equal to b raised to a different power, those two powers are not actually different, but they are equal. Now they're going to look different because the whole point of this is to solve for a specific variable, but as long as you can get both sides as simple as just the same base raised to different looking powers, you can take those exponents and just set them equal to each other, right? We can kind of just eliminate the whole exponential part of the equation. So if I have something like 2, let's say 5 to the 7 power equals 5 to the 2x power, I know that since the bases are the same, those exponents must be equal to each other. So we'll do an example here. Because 5 to the 7 is equal to 5 to the 2x, we can take this and convert it and get rid of those bases and just say that these exponents 7 must equal 2x. And then from there, we can solve for x, right? We could just divide both sides by 2 and say that x is equal to 7 over 2. Right, so that would be an example where we are trying to solve for this x, but it's in an exponent to begin with, and we don't really want to deal with. I mean, eventually we're going to have to take the log of both sides to get this exponent down from the exponent. But if you can simplify it to a point where both sides are just some base raised to, or the same base raised to some powers, you can just take these powers and set them equal to each other, right? So let me talk about this example here. We're trying to solve this expression for x. Now, it immediately starts not looking exactly like the beginning of this, using like bases left side of this if and only if statement, because we don't necessarily have the same base on both sides, right? The right side is kind of a weird quotient that we're working with, and the left side is a power of 3. So if the left side is a power of 3, we kind of want to make the right side look like a power of 3 as well. So what we can do is we can just focus on the right side and convert this or rewrite it in a way that it is just 3 raised to some power, and then we'll have 3 raised to something equal to 3 raised to something else, and we can get rid of those bases using this idea from here. So the left side we're going to leave alone. We're going to say 3 to the 4x minus 7 equals, and now I have a quotient of 3's. I have a 3 to the 2x divided by 3. This 3 in the denominator is essentially a 3 to the first power. And what do I do with those exponents if I'm dividing expressions with the same base? The laws of exponents say, what do we do with these exponents?
Subtract.
We subtract. Good. So we can rewrite this as a 3 to the 2x minus 1. Right? And now I've gotten it to a point where it's the same base on both sides, and there's nothing else to kind of dilute that situation. Right? We have simply just the same base on both sides raised to some powers. And now we can go from this. We can use the if and only if statement from out there and say that this means that 4x minus 7 must equal 2x minus 1. And then we're in very basic algebra here. We can subtract the 2x to the other side. So we'll end up with subtract the 2x and add 7 to both sides to get to isolate the x on one side. So we'll have 2x equals 6. And then divide by 2 to get x equals 3. Right, so x must be 3. 3 is the only number for x that makes this equation true. Right, that's what we just solved for. All right, so this is your first tool for dealing with both. If both sides are exponential and you can somehow get both sides to be an exponent of the same base, we want to use this one-to-one property of exponential functions. So you'll do a couple of examples with that. Now, you'll run into situations where it is impossible to get both of these, the 5 and the 4, to be the same base, right? Looking back at this one real quick, these are not necessarily the same base, 8 and 16, but they can be written as powers of the same base, right? 8, I guess I'll give you a hint on this one. 8 can be written as a power of 2. It's 2 to the third. And 16 can also be written as a power of 2 in 2 to the fourth, right? So you're going to do something where you write both sides as a smaller number raised to a power. So as long as you can get both sides to be in terms of the same base, you'll be able to use that one-to-one property in order to solve, in order to get rid of those bases, drop the exponents down, and set them equal to each other. Now, you're going to run into situations where you can't do that, where you have 5 to the x plus 2 on one side and 4 to the x on the other side, and you want to solve for x. You cannot get 5 and 4 to be in terms of a common base. So what we're going to do is we're going to take logarithm of both sides. So we're going to apply a logarithm to both sides, and the reason for doing that is that allows us to take exponents and make them no longer exponents, right? Remember the power rule for logarithms says if I have a log base b of a to the n power, I can take that n and I can move it to the front and say n times log base b of a, right? That power rule is going to be useful for solving these, but the first thing we're going to do is we're going to take this and we're going to essentially log both sides. And when you log both sides, you get to choose what kind of log you want to use. You can use a log base, anything you want. Generally, we stick to the standard log if we don't want to write a base, or we can use natural logarithm because it's less writing for us. So if I take the natural log of both sides, this is what it looks like. I'll say natural log of 5 to the x plus 2 equals the natural log of 4 to the x. So I take the logarithm, the natural logarithm of both sides. And in doing so, I can now use this power rule from before, and I can take these exponents and I can move them to the front of each logarithm. So I'll have x plus 2 times natural log of 5 and x times the natural log of 4. Sorry, I kind of glazed. I didn't really talk about this as much, but if you have the same log on both sides, you can essentially get rid of it and say a is equal to b. Right? If I have a log of a equal to log of b, we can kind of just get rid of the log on both sides. This is kind of like the one-to-one rule for exponents, but this is the one-to-one rule for logs. So if you have the same log base on both sides, you can get rid of those logs. Alternatively, you can go from an equal expression and kind of just add logs to both sides, which is what I've done here. I've taken an expression that is already equal, and I've introduced a natural log to both sides. So that is how I was able to put an ln on both sides. And now we have a more of a basic expression that we can kind of try to solve for x now. This ln of 5 needs to distribute into this parenthesis because we have an x plus 2 multiplied by natural log of 5. So that's going to turn into x times natural log of 5 plus 2 times natural log of 5 equals x times natural log of 4. And now we're dealing with these natural logs dispersed all over the place. They're just numbers. Right? If you plug in natural log of 5 into your calculator, that's just a number. Right? If you plug in natural log of 4 into your calculator, that's just a number. So this is a number times x and a number times 2 and a number times x again. How we solve these is we're going to treat these like numbers and just start isolating the x. So we want all of the x's on one side and we want all of the pure numbers on the other side. This 2 times natural log of 5 is just a number. There's no x there to deal with. So I'm going to leave that over there and I'm going to subtract this one to the other side. So minus x ln 5. This is kind of like doing 3x minus 2x, right? We have a number times x minus a number times x. We can essentially factor this x out and rewrite it in a way that it's a number times a number minus a number times x. So these go away on the left side. We get 2 ln of 5. I'll just rewrite this x natural log of 5 because you can't combine them right away. You can't combine them nicely. All we can do is factor out the x because you have x times something and x times something else. So what I can do is I can factor out that x. So 2 ln of 5 equals x times ln of 4 minus ln of 5. So I factored out the x. And now I can divide this whole thing over to the other side. So my x here will equal 2 natural log of 5 divided by natural log of 4 minus natural log of 5, which is a number. If you plug that into your calculator, it'll be a number. But we can stop there because we're not using calculators. The only thing you could do is take this 2 and put it back up as an exponent on top of the 5 and rewrite that as a 25. But I think this is just as good, leaving the 2 where it is. Any questions on any of those steps in that example? Okay, next thing we're going to talk about is how to use the definition of logarithms to solve these types of expressions or equations. We have an equation example here. The definition of logarithm is how we were switching from a logarithmic expression to an exponential expression. So taking this log and trying to move it to the other side, we take the base to the other side as a base, and it pushes whatever's on the other side into the exponent, right? So we're going to have x equal to b to the y. So we take this log base to the other side, it pushes whatever's over there into the exponent. But before we can do that, we need a log by itself on one side of our equality. So we have a log here, but there's also this 2 and this 3 that we want to deal with before we use this definition. So we want to isolate this log first, and there's a couple ways we can go about doing that. First things first, let's get rid of this 3. Let's subtract 3 from both sides. That'll be the first step in getting this log isolated. So it'll be 2 log of x plus 1 equals 4. And from there, there's 2 things we can do. We can either divide both sides by 2 to get rid of this 2, or we can take this 2 up into the exponent of the logarithm. I think it's better to just get rid of the 2 by dividing, but you can go the other way as well if you'd like. So I'll divide by 2. That'll leave me with a log of x plus 1 equals 2. And how we use the definition of logarithms here, remember this is a log base 10. We're going to take that log base, push it to the other side, and we're going to push this 2 up into its exponent. So when we switch to exponential notation, we will have x plus 1 left on the left side because the log is now gone, equal to 10 squared. Right, that's the definition of a logarithm. That's what a logarithm is. So now we have x plus 1 equals 10 squared, which is 100. We can subtract 1 from both sides and get x equals 99. Right, and if you want to check your answer here, it's pretty easy. You can take this 99 and plug it into your original equation. Log of 99 plus 1 is a log of 100. Log of 100 using some properties of logs will end up being 2. So this will end up being 2. 2 times 2 is 4, plus 3 does equal 7. So you can check your work by taking this answer and plugging it back into the original equation. So the definition of logarithm is given to you again here. The base, how the base moves to the other side and pushes everything to be an exponent. Use the one-to-one property of logarithms. Okay, we'll do an example here where we use the one-to-one property of logarithms. So we're getting, if I have, I foreshadowed this earlier, I wrote it down. If I have the same log on both sides of an equal sign, we can essentially get rid of those logs because they're doing the same thing to both sides. So we can undo that same thing and just say that m must equal n from both sides. So you can essentially eliminate those logs. Now, in order to use this, you need just a single log with the same base on both sides. Here in this example, if we take a look at it, we have a log minus another log equal to another log, right? We don't necessarily have this exact setup yet. So what we can do is we can combine what we've learned so far with expanding or condensing or power rules or quotient rules or product rules and any other properties of exponents that we've learned so far to kind of get to this form where we have the same log base on both sides, and that's the only thing we have on both sides. So I really want these two logs to be one log. How can I combine them into a single log?
Using the quotient rule for
Good.
log.
Good. We're going to use the quotient rule. I'm just going to say condense here. And then if it's a sum, we'll multiply the insides. If it's a minus, we'll divide the insides, right? So when we're condensing here, this condenses into a single log of, it's going to be a quotient, like you said, because we have a minus sign here. So we're going to have a fraction, excuse me, any positive log, like this one, its inside is going to go in the numerator, and any negative logs inside is going to go in the denominator. So we'll have 3x minus 2 in the numerator and a 2 in the denominator. And that's equal to log of x plus 4. And now I have something that looks like the one-to-one property for logarithms. I just have a single log on both sides, which means these insides must be the same. So we're going to take this and we're going to get rid of the logs. We're going to say 3x minus 2 divided by 2 must equal x plus 4. And now we can go back to what we know about algebra to solve this. We probably want to start with getting rid of that 2 in the denominator, multiply both sides by 2. Here they cancel out. We get 3x minus 2 equals 2x plus 8. We distribute the 2 on the right side. And then we're going to subtract the 2x, add 2 to both sides, and we'll be done, I think, because we get x equals 10. Cool. So you might need to condense before you use this property. You might need to use the power rule before you use the property. You just need to somehow get to the same log base on both sides. There's a note down here that is pretty important, so I'm going to put a star next to it. When solving an equation involving logarithms, always check to see if the answer is correct or if it's an extraneous solution. Extraneous solutions are going to be a big deal when it comes to logarithmic equations. So I'm actually going to erase this box around this answer because we want to check it first. The reason why we have to check the answers of logarithmic equations is because of the restricted domain of logarithms. Remember that if the number inside of a logarithm is negative, that is outside the domain. We cannot plug in negative numbers. We cannot plug in 0 into logarithms, meaning when I get this x and I go back and plug it into all of my x's, if somehow one of these logarithms turns into like a log of -3 or something, then that answer is an extraneous solution and it is not a solution. right? We call them extraneous solutions when they're kind of extra solutions that don't make sense in the scope of the problem. So we have to take this 10, we got to plug it back into our x's to make sure we don't get anything outside of the domain, and to make sure that we get the two sides are equal to each other. So we'll take this answer and we'll plug it back into the original equation to check. So let's do the check here. We'll plug in 10 into these logs. So we get log of 3 times 10 minus 2 minus log of 2 equals log of 10 plus 4. 3 times 10 is 30, minus 2 is 28, so I get log of 28 minus log of 2 equals log of 14. Everything is good so far. These are all positive numbers inside of the logs, so I'm feeling pretty confident about the answer of 10 here, but let's just go ahead and condense these two into a log of 28 divided by 2 equals log of 14. And 28 divided by 2 is 14, so log of 14 equals log of 14. And 14 equals 14. I'll put a check mark next to that, and then we'll go back and box our answer of x equals 10. A lot of times the check won't fall apart in like the algebra part of it. It'll usually fall apart where you'll have a negative number in one of the logs, or you'll have a 0 inside one of the logs, and that's outside of the domain. So that's undefined. If you try to put that into the calculator, it'll give you an error. Like a log of a negative 14 would be undefined, right? So we're looking for things like that for this answer to not make sense, right? If it's a log of a negative number, you say this is not a solution. Okay, just remember to check your answers, especially when you're doing a logarithmic equations. All right, and then in 7.7, I'm going to give you a formula for half-life that you can use. It's not really written down here, so I'll write one for you that we can use. We'll put it up here. We're going to say n equals n sub 0 times 1/2 to the t divided by t sub 1/2. And let me explain what each of these things are. N is the ending amount of whatever substance you're working with. N sub 0 is your starting amount. One half is 1/2. It's representing half-life. So I guess we should title this, huh? This is the half-life half-life formula. The t is just time, and t sub 1/2 is the half-life of the substance. So there's a few things. There's 4 kind of variables in the formula, but I'll do an example to show you how we use the formula in this example here. So the question will either tell you what the half-life of a substance is, or it'll be your job to find that half-life. Either way, we're either looking for this t sub 1/2, or it's given to you in the question. So when the question says the half-life of gallium-67 is 80 hours. That means that this 80 hours is my t sub 1/2. Right, so let's identify that as our half-life. Part A says determine a formula for the amount of gallium-67. A, so they want us to use the variable A there for the amount remaining after T hours if we start with a 1,000-gram sample. So we're not given a time, but we're told that we're just going to write the formula for T hours. And A is going to be our amount left, our ending amount. So A is our ending amount. So we're going to write this as A equals our starting amount, which is a 1,000-gram sample. That is our n sub 0. So we'll have 1,000 grams to begin with. And then we'll multiply that by 1/2. Excuse me. 1/2 to the t divided by the t sub 1/2, which will be t divided by 80. And that is our amount left after t hours. Okay, so you should be able to use this formula with any kind of given situation where you plug in certain numbers. Maybe you know the ending amount and the starting amount, and you're trying to find time, or maybe you know how much time it took to go from a starting amount to an ending amount, and you're looking for the half-life. There are different variations of half-life questions that you could work with. Decay. So this part B says, how long will it take this 1,000-gram sample to decay by 10%? And then part C says, how long will it take this 1,000-gram sample to decay to 10%? This is essentially saying by 10% means lose 10% of weight or mass. And this is reduce down to 10% of its weight. So one of them, the first one, decay by 10%, is talking about losing 10% of its weight. Decay to 10% means you're dropping all the way down to only 10% remaining. Actually, that might be better to write here. 10% remaining. Whereas if you decay by 10%, the amount remaining is 90%. Right? The remaining amount is going to be your ending amount, which you have to figure out from 90% remaining or 10% remaining. Okay, I'm going to stop there. We won't continue into 7.7 until Wednesday. You have quite a few